Okay, Cap BC, lesson 410 or 409. I guess it just depends on the timing of our schedule and stuff. I could give it to you either day. This is the last lesson for this unit. So I'm going to talk about polar arc length. So that's the length of the polar curve. And we've gotten into this a little bit already this year with parametric. So I don't know if you guys remember with parametrics what the length of a parametric curve was, but it was based off of integrating speed because that gives you distance, right? So we're looking for like total distance. But in two dimensions, it got a little more complicated, and speed was the square root of dx dt squared plus dy dt squared, or the velocity in the x direction, the velocity in the y direction squared. And it was kind of based off this idea of like the hypotenuse of a right triangle. So I'm just putting that out there because that's what we've done recently. But now let's take a look at polar, and let's see if we can figure out how to derive this just to start off with, because I think you guys could be good with this making sense. So I'm going to kind of draw sort of a generic polar curve. And, they're just, very round. And the way that the curve is graphed is sort of, in this radial kind of fashion, right? And that's sort of how we developed our idea of how to find the area, was with these slices. Now, what we could do is we could say, well, what's the length of one of these slices? And then we could integrate and accumulate all of them together. So let's look at one slice on its own. We'll kind of exaggerate it, make it a little bigger. Okay. And we want to find the length of this. Now, it's an arc length, but it's not a perfect circular arc length. I mean, it's a curve. What we could do, though, to estimate it is we could say, well, let's just find the length of this straight line connecting the two edges of the arc length. Now, that's an estimate, and if we make them infinitely small, it's going to start, if you just did one for this whole arc, it'd look really bad. But if you started doing it for all of these, it'd start to look closer and closer to the actual curve. And so if we do infinitely thin slices, infinitely small, we call these I think it's like a secant line, for the curve. So we're going to use that. Now the next trick is, how do we figure out the length of that line? So what we're going to do is we're going to draw a little right triangle, and it's the hypotenuse of that right triangle. And this is a small change in y with respect to theta, because we want things to be in terms of theta, because this is theta, this is d theta, right? So this is a small change in y. As theta changes, the y coordinate changes, and then this is a small change in the x direction, dx d theta. And so then the hypotenuse would be, from Pythagorean theorem, dx d theta squared plus dy d theta squared. And then you take the square root. I mean, that looks a lot like what we use for parametrics, and we could do that. So, we could use that as our length formula. But I think we're going to try and tweak it a bit to make it a little easier to use. And it might not seem that hard to use right now, but I'll show you. So So this is our formula. Now, just as an example, let's, well, not as an example, we're going to sort of tweak this. So the x that we're using here would need to be in terms of theta, right? So, so x equals r cosine theta, right? And the y would be y equals r sine theta. And we are going to keep this generic. And I'm going to go ahead and do something I kind of I've shown you a couple times, but kind of discourage you from looking at. Let's go ahead and find dx d theta in terms of with r's in it. And so it'd be negative r sine theta, because the derivative of cosine is negative sine, plus r prime cosine theta. So it's a little product rule, right? And so that's what would end up going in right there. And dy d theta would be r cosine theta plus r prime sine theta. And so that is going to go in right there. And let's go ahead and plug it in. Okay. I mean, usually we would have more specific, R equation, and we could do all this work. I mean, that's what you would do. But I'm looking for something to make easier. Okay. Make things easier. So we're going to plug negative r sine theta plus r prime cosine theta, and it gets squared. And then r cosine theta plus r prime sine theta, and it gets squared. And then we have a d theta. Okay. Now let's go ahead and FOIL this out. Let's try and simplify this. So here we're going to get positive r squared sine squared, and then we're going to get minus 2r r prime sine theta cosine theta, and then we're going to get plus r prime squared cosine squared. That's just for the first one. And then the next one is going to be r squared cosine squared plus 2r r prime sine theta cosine theta plus r prime squared sine squared. And then you have a d theta. Okay, so I'm just multiplying all this out. Now let's see if we can simplify anything. These two terms actually just canceled each other out. Okay. And then what we could do is we could say, well, let's take the r sine squared and r cosine squared and group them together and factor out the r squared. And let's do something like that with the r prime squared, cosine squared, and r prime. So I'm combining those together and factoring out that part of it. Okay, now here's the deal. You guys see anything? Pythagorean trig identity. That's going to be 1. That's going to be 1. And so what we get is we get r squared plus r prime squared d theta, which is a lot easier to use. Just otherwise you're doing all this work every time. You're going to go through all this, and it's going to be more complicated because there's going to be an actual r there. I mean, it's going to be a mess. You don't want to do it that way. You want to do it this way. This comes from that. I mean, that one was kind of easy to understand. It's just like a little, it's the length of the secant line, which is the hypotenuse of the little right triangle. But we can manipulate it into looking like this. So there's another version that we could write. That's the same thing, just different notation for the derivative, just in case that r prime is potentially, So that's it. This is what we want to use. I mean, it almost looks exactly, I mean, this one would be easy to remember because it looks almost exactly like a parametric one, but it's just really hard to use. So it still has a derivative inside squared, and it has an r squared, so it has a square root. So it still is very similar to the other one. So we do a quick example and show how this works. So r equals 1 plus cosine theta. Just do a quick, simple cardioid. I'm going to do a quick sketch. Not that I don't really think the sketch is going to help us on these ones, but why not? 2, 1, 0, 1, 2. We're pretty good at these anyways, right? Okay, there's your cardioid. So if we wanted to find the length around this cardioid, it seems like it'd be some kind of weird number. But so the arc length, we're going to use this new formula that we just wrote up above. We're going to integrate 0 to 2 pi, so it depends on how much it takes to graph the whole shape. Square root of, now what we need r, which you already have. That's easy. Plug that in, squared. But then we need r prime or drd theta, and that's going to be negative sine theta, so that's pretty easy to find. And that's the setup. Now let's see if we can, how far we can get maybe without a calculator. Let's see. That would be 1 plus 2 cosine theta plus cosine squared theta plus sine squared theta, which we can probably replace with 1 minus cosine squared theta. And so then, let's see. The cosine squareds cancel. 2 plus 2 cosine theta. It's getting pretty simple, but we can't factor that. So in our calculator, just do it on the calculator. Now I'm not going to do it in polar mode. Usually we're not going to use polar mode unless you want to draw graphs, I think. So I'd do it in function mode, and I would just integrate. I just put x's where the thetas are because it's single variable math. 9 fnt square root of 2 plus 2 cosine, put x in, close, comma, x, comma, 0, comma, 2, pi. He's ready for the horrible, ugly answer. 8! Wow, that's really nice. So, there you go. So that's it. That's that last little thing to add to things we know how to do with polar. So, try the assignment.